Hello, in today's video, I'll be solving questions on A to Equilibria from October-November 2019, paper 4-1. Question 5. Silver sulfide, Ag2S, is very insoluble in water. I. Write an expression for the solubility product, Ksp of Ag2S solid. When you have a question like this, the first thing to do is to write the equilibrium dissociation equation of the salt. So we have Ag2S solid dissociate to give 2Ag plus aqueous plus S2 minus aqueous. Now the Ksp is equal to the multiplication of the concentrations of the ions of the salt raised to the stoichiometric amount. So Ksp is equal to concentration of Ag plus squared, as the stoichiometric amount of the Ag plus is 2, times concentration of S2 minus. The stoichiometric amount of the S2 minus is 1. So we leave this equation as this. II. The solubility of Ag2S solid in water at 298 Kelvin is 1.16 times 10 power minus 17 mole per decimeter cube. Calculate the numerical value of the solubility product Ksp of Ag2S solid at 298 Kelvin. When you have a question like this, the first thing to do is to write the equilibrium dissociation equation for the salt. And so we have Ag2S solid dissociate to give 2Ag plus aqueous plus S2 minus aqueous. To find the Ksp, we need the concentrations of the ions of this salt. But you have been given the solubility or the concentration of the Ag2S salt as 1.16 times 10 power minus 17. And so we write that under this 1.16 times 10 power minus 17. The mole ratio between the salt and the Ag plus ion is 1:2. So it means this will be 2 times 1.16 times 10 power minus 17, and that of the sulfide ion is just 1.16 times 10 power minus 17, since the mole ratio between the sulfide ion and the salt is 1:1. Now our Ksp equation was written as this, and so it's just a matter of substituting the concentrations of these ions from here into the equation. The concentration of Ag plus ion is 2 times 1.16 times 10 power minus 17, which is equal to 2.32 times 10 power minus 17 squared times the concentration of the sulfide ion, which is 1.16 times 10 power minus 17. And so if you do this, you get Ksp as 6.24 times 10 power minus 51. In case they ask you to find the units of the Ksp, that will be mole decimeter minus 3 squared times mole decimeter minus 3. This gives us mole squared decimeter minus 6 times mole decimeter minus 3. And if you multiply this together, you get mole exponent 3 decimeter minus 9. I. Calculate the minimum volume of water needed to dissolve 1.00 grams of Ag2S solid under standard conditions. Concentration is given as C is equal to N over V. The concentration of this salt was given in the question as 1.16 times 10 power minus 17 mole per decimeter. Now we need to find the amount of the salt and the amount is given as mass over molar mass. The mass has been given as 1.00 grams, and so we need to find the molar mass. So molar mass of Ag2S is equal to the atomic mass of Ag, which is 108 times 2, plus the atomic mass of sulfur, which is 32. And this gives us 248 grams per mole. So the amount of Ag2S is 1.00 grams divided by the molar mass 248 grams per mole. And this gives us 4.03 times 10 power minus 3 mole. Volume from this equation is giving us V is equal to amount over concentration. The amount that we solved for is 4.03 times 10 power minus 3 mole, and the concentration given in the question is 1.16 times 10 power minus 17 mole per decimeter cube. So the volume is equal to 3.5 times 10 power 14 decimeter cube. B. Bromic 1 acid, HOBr aqueous, is a weak acid. Its Ka is 2.0 times 10 power minus 9 mole per decimeter cube. I. Calculate the pH of 0.20 mole decimeter cube HOBr aqueous. First, write the equilibrium dissociation equation for the acid as HOBr aqueous gives OBr minus aqueous plus H plus aqueous. The concentration of the acid was given as 0.20 mole per decimeter cube, but we don't know how much of this dissociated to form the ion, so we put X and X here. Now the Ka is equal to concentration of OBr minus times the concentration of H plus divided by the concentration of the acid HOBr. Ka is 2.0 times 10 power minus 9, and the concentration of the OBr minus ion is the same as the concentration of the H plus ion, and they are both X, and so X times X will give us S squared divided by the concentration of the acid, which is 0.20. So S squared is equal to 2.0 times 10 power minus 9 times 0.20. So we find the square root of both sides. And so X is equal to 2 times 10 power minus 5 mole per decimeter cube. pH is given as negative log of H plus ion concentration. And notice that the H plus ion concentration is the same as X. And so since we know the value for X, we just substitute that into this equation. So we have negative log 2 times 10 power minus 5. And so our pH is 4.7. II, 5.0 centimeter cube of 0.20 mole per decimeter cube potassium hydroxide KOH are added to 20.0 centimeter cube of 0.20 mole per decimeter cube HOBr aqueous. Calculate the pH of the buffer solution produced. The first thing to do is to write an equation between the acid HOBr and the base KOH. And you know, when an acid and a base react, it gives you salt and water. And so we get our salt as KOBr, as the metal from this base displaces the hydrogen of the acid. plus H2O. All of them aqueous, 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 and liquid for water. Now we need to find the amount of both the acid and the base reacting in this equation. And amount is given as C times volume, as we know the volume of and the concentration of both the acid and the base. And so amount of the potassium hydroxide is equal to the concentration, which is 0.2 times the volume, which is 5, but we convert that to decimeter cube. So we divide this by 1000 or multiply this with times 10 power minus 3. And so if you do this, you get 1 times 10 power minus 3 mole. And again, we also find the amount of the acid, HOBr, which is equal to the concentration and the volume of the acid. So 0.2 times 20 times 10 power minus 3. So we do this to convert the 20 centimeter cube to decimeter cube. And then you get the amount to be 4 times 10 power minus 3 mole. And so over here, at the start of this reaction, so initial, the concentration of the acid is 4 times 10 power minus 3 mole. And that of the base is 1 times 10 power minus 3 mole. So at the start, these were not formed, so 0, 0. But at equilibrium, the concentration, the amount of the acid and the base will react to give product. And so we can see that since this one has a small amount, it is the limiting reactant. And so it will totally be consumed in this reaction. So by the time this reaction ends, the amount of this will be 0. But this will still have some amount left. So if you subtract the 1 times 10 power minus 3 from 4 times 10 power minus 3, we get 3 times 10 power minus 3 mole left at the end of the reaction. Now, to determine the amount of the salt, we use the amount of the limiting reactant and the mole ratio between that reactant. The limiting reactant is the potassium hydroxide. So the mole ratio between the potassium hydroxide and the salt as well as the water is 1:1. And so it means that the amount of both the salt and the water will be 1 times 10 power minus 3, 1 times 10 power minus 3, because you are very much assured that it is this amount that is completely consumed to give you the product. Now we know that the pH of a buffer is given as pKa plus log concentration of the salts divided by concentration of the acid. So now we need to find the concentration of both the acid and the salt in this final solution. So concentration is equal to amount over volume. And for the salt, the amount is 1 times 10 power minus 3 divided by the total volume of solution. Because this time around, the moment you add these two solutions together, the concentrations of the acid and the salt are not going to be as the initial concentrations since we have increased volume. So we need to find the concentration in the final volume. And so the final volume is 25 centimeter cube, but we convert this to decimeter cube, so that will be times 10 power minus 3. And this gives us 0.04 mole per decimeter cube. The concentration of the acid, HOBr, is also equal to 3 times 10 power minus 3 mole divided by the total volume of solution, 25 times 10 power minus 3. And this also gives us 0.12 mole per decimeter cube. Now we know that pKa is equal to negative log of the Ka of the weak acid. And so this is equal to negative log 2.0 times 10 power negative 9, and this is equal to 8.70. So our pH is equal to the pK, which is 8.70, plus log concentration of the salt, and the concentration of the salt is 0.04 divided by the concentration of the acid, which is 0.12, and so the pH gives us 8.22. Please subscribe to this channel and click the notification bell. See you in the next tutorial.